The physical timeline to build a semiconductor fab is no longer gated by cleanroom construction or lithography tool delivery. It is gated by the cryogenic cold boxes required to supply ultra-high purity nitrogen. Cryogenic cold box lead times escalated from 16 months in 2018 to 34 months in 2023. This delay is driven by structural backlogs in high-alloy aluminum plate-fin heat exchanger fabrication. In 2021, air separation unit lead times crossed the typical fab construction window of 28 months. This shift placed industrial gas infrastructure on the primary critical path for new semiconductor projects. Plate-fin heat exchanger backlogs peaked at 90 weeks in 2023, up from 22 weeks in 2018. This reflects extreme concentration in specialized vacuum brazing and metallurgical welding capacity. Ultra-high purity nitrogen consumption scales nonlinearly as transistors shrink. For a standard facility processing 50,000 wafers per month, demand rises from 35,000 cubic meters per hour at 28 nanometers to 115,000 cubic meters per hour at 3 nanometers. This gas must achieve 99.9999% purity to prevent wafer oxidation in process chambers. Even part per billion levels of moisture contamination will ruin entire production runs. Operating a 3 nanometer air separation unit requires a continuous electrical load of 38.5 megawatts. This massive power draw ties operational costs directly to regional grid stability. To mitigate grid or plant downtime, advanced fabs require up to 46,000 tons of liquid nitrogen backup storage. This volume is necessary to guarantee a minimum 72-hour emergency purge capability. The global supply of advanced cryogenic air separation units is highly consolidated. 3 industrial gas multinationals control 72% of the market and over 85% of advanced engineering, procurement, and construction capacity. Lind leads the sector with a 32% market share and is managing 14 active Mega-Fab projects. This concentration stretches specialized cryogenic engineering teams to their physical limits. Regional Chinese firms hold 12% of the general market, but lack the technical capacity to deliver high-purity nitrogen at scale. Their engineering capability is rated at just 4.5 out of 10. Consequently, Western and East Asian semiconductor sovereignty plans remain structurally dependent on a narrow oligopoly of industrial gas engineers. The primary dry bulk terminals at Ningbo-Zhoushan are operating far beyond their engineered limits. Shilanghu and Beilan terminals both breached 100% nominal capacity in 2021. By 2023, utilization reached 116.4% and 118.1% respectively. This systemic overload has triggered a nonlinear spike in vessel queuing. Average anchorage wait times for Capesize carriers rose 42% year-on-year to 63.2 hours in 2023. The bottleneck is driven by a 28% increase in very large ore carrier arrivals over 5 years. This influx has completely outstripped local berth expansion rates. Global shipping economics favor massive scale, but physical bathymetry imposes a hard limit. Fully laden Valemax ore carriers of 400,000 deadweight tons require a minimum draft of 23 meters. This draft restricts their transit to a highly compressed 2-hour daily tidal window in the Kayantang estuary. Standard Capesize vessels face similar constraints with a 4-hour daily transit window. This restriction results in average delays of 48.2 hours per port call. Smaller Panamax vessels enjoy unrestricted 24-hour access, but they carry up to 80% less cargo per transit. This creates a structural trade-off between transport efficiency and port accessibility. The physical limits of direct discharge have plateaued near 124 million metric tons. To bypass this bottleneck, operators are forced to execute midstream ship-to-ship transshipments onto smaller vessels. This transshipment volume surged 223% to 58.9 million metric tons in 2023. Double-handling cargo introduces severe operational friction and material degradation. It drove a landed cost premium of $4.85 per metric ton of iron ore in 2023. This structural premium directly erodes the operating margins of domestic steel producers. It demonstrates how bathymetric constraints inflate heavy industrial input costs. The rapid transition to lithium-iron-phosphate chemistry has fundamentally altered the physical requirements of grid-scale energy storage. Legacy forced air cooling is no longer technically viable for high-density installations. Liquid-cooled architectures have escalated from 10.2% of global installations in 2020 to an estimated 82.5% by 2026. This shift is driven by the need to maintain cell temperature variance within a strict plus or minus 2 degrees Celsius window. Exceeding this thermal threshold accelerates capacity fade and risks catastrophic thermal runaway. Maintaining this precise temperature window reduces battery degradation rates by up to 25%. By 2026, liquid-cooled systems will account for 175.5 gigawatt-hours of the projected 212.7 gigawatt-hour global market. This makes specialized thermal management the primary gating factor for grid deployment. This technological pivot has transferred the primary bottleneck of grid storage from battery cell manufacturing to specialized HVAC engineering. Chiller manufacturers are struggling to secure core industrial components. Lead times for industrial scroll compressors reached 15 months in 2024, representing a 233% increase from 2020. This delay is exacerbated by intense competition from the rapidly expanding data center cooling sector. Variable frequency drive pumps now require a 14-month lead time, disrupting just-in-time manufacturing models. These component shortages have created a global deficit of 18,500 BESS-specific chiller units this year. This equipment deficit directly stalls the commissioning of approximately 22 gigawatt-hours of grid-scale storage projects. The physical constraint is no longer lithium supply, but the mechanical components of thermal regulation. Physical shortage of liquid cooling chillers translates directly into severe project delays and financial penalties for grid developers. Large-scale installations exceeding 200 megawatts now face average commissioning delays of 14.5 months. Without operational chillers, developers cannot complete mandatory OL 9540 safety certifications. This regulatory barrier halts final grid interconnection agreements, leaving completed battery assets idle. The financial consequences of these delays are severe. Liquidated damages for delayed grid connections averaged $45,000 per day for large-scale projects in 2024. These mounting penalties directly erode developer internal rates of return. The bottleneck demonstrates that the transition to renewable power grids is structurally bound to heavy industrial HVAC supply chains. The aerospace superalloy supply chain is structurally fractured by a geographic decoupling of raw extraction and chemical refining. South Africa controls 44% of global chromite ore mining, but holds only 5% of ultra-low-carbon refining capacity. Conversely, China dominates the high-purity refining node with a 55% global capacity share. This dominance exists despite China possessing virtually zero domestic ore reserves. This extreme concentration exposes Western defense industrial bases to single points of failure. Scandinavia represents the West's primary refining alternative, holding 20% of global capacity. This Northern European node relies entirely on imported ore, leaving it vulnerable to maritime logistics disruptions. Refining ultra-low-carbon ferrochrome is fundamentally an energy arbitrage business. Smelting a single metric ton requires up to 4,500 kilowatt-hours of electricity. This makes power the dominant variable cost in major refining hubs. South Africa possesses a nominal cost advantage at $2,800 per ton. However, systemic electrical grid instability and load shedding limit local smelter utilization to below 60%. Norway leverages stable hydroelectric power to lower energy costs to $850 per ton. Yet, high labor overhead and the cost of importing raw ore offset these utility savings. This cost structure prevents easy diversification away from carbon-intensive refining hubs. Upstream metallurgical bottlenecks propagate directly into downstream defense procurement delays. Spot prices for high-purity ferrochrome surged over 129.7% between 2020 and 2024. Prices peaked at $4.25 per pound. This price spike reflects energy crises in Europe and power rationing across Chinese smelting hubs. The material deficit has doubled lead times for critical nickel-based superalloy forgings to 56 weeks. Procurement cycles for high-performance, single-crystal turbine blades now stand at an unprecedented 80 weeks. These compounding delays directly stall military jet engine assembly lines and commercial aerospace backlogs. The defense industrial base remains highly vulnerable to these specialized material nodes. Advanced semiconductor manufacturing relies on chemical inputs that are highly concentrated in just 3 regions. Japan, Taiwan, and the United States control nearly 89% of global ultra-high-purity ammonia purification capacity. This 7N grade gas is essential for depositing silicon nitride dielectric layers in advanced logic and memory chips. Without it, chemical vapor deposition processes cannot proceed. While global capacity reached 34,300 metric tons in 2024, the rest of the world produced just 3,800 tons. This geographic concentration creates an immediate bottleneck for European and domestic U.S. fabrication initiatives trying to diversify their supply chains. Primary vulnerability in this chemical supply chain is not just purification, but specialized logistics. Ultra-high-purity ammonia must be transported in dedicated, electropolised stainless steel ISO containers to prevent contamination. Between 2019 and 2024, global demand for this gas rose 63.3%. However, the specialized ISO tank fleet expanded by only 26.2%, creating a structural transport deficit. A standard Mega-Fab processing 50,000 wafers per month consumes 4.0 metric tons of this gas every week. Because these facilities maintain minimal on-site inventory, any transit delay exceeding 10 days threatens to halt cleanroom operations entirely. Long-distance maritime transit introduces a hard physical limit to chemical purity. Over time, microscopic gasket permeation and container wall outgassing contaminate the cargo. Moisture levels inside the ISO containers rise from 10 parts per billion at day 0 to 170 parts per billion at day 30. The critical threshold for 7N purity is breached after approximately 22 days of transit. Beyond this point, the gas becomes unusable for advanced chemical vapor deposition. Utilizing degraded ammonia introduces oxygen and metal impurities that cause lattice defects, reducing final wafer yields by up to 18%. This chemical degradation makes long-distance shipping highly risky. It proves that semiconductor manufacturing sovereignty requires localized chemical purification, not just domestic lithography tools. The global supply chain for space-qualified microelectronics is bottlenecked at the substrate level. A single European firm, Soitec, controls 89.5% of the radiation-hardened silicon-on-insulator wafer market. This dominance relies on their proprietary smart cut technology. Alternative manufacturing methods, such as separation by implantation of oxygen, have remained stagnant for 6 years. As Western nations modernize their military satellite networks, they run directly into this single point of failure. The entire defense space architecture depends on a single commercial entity in France. The transition from large geostationary satellites to proliferated low Earth orbit constellations has broken the microelectronics supply chain. Active and planned military satellites tracked by Western agencies surged from 120 in 2018 to 1,150 in 2024. This 858% increase has overwhelmed specialized semiconductor foundries. Average procurement lead times for space-qualified chips have escalated from 24 weeks to 104 weeks. These accredited, ITAR-compliant facilities are operating at over 95% capacity utilization. The mismatch between rapid orbital deployment schedules and multi-year semiconductor manufacturing cycles is widening. Standard bulk silicon cannot survive the intense radiation of low Earth orbit. Space-based defense assets require specialized silicon-on-insulator substrates to prevent catastrophic failure. Advanced silicon-on-insulator wafers with thick buried oxide layers increase total ionizing dose tolerance to 10 million rads. This represents a 200-fold increase over standard bulk silicon. Dielectric isolation also raises the single event upset threshold to over 75.0 units. This design eliminates parasitic paths, providing absolute immunity to single event latch-ups. These physical performance advantages make specialized silicon-on-insulator substrates completely non-substitutable for national security space programs. The expansion of the port of Gdansk Baltic hub has decoupled marine handling capacity from landside evacuation capabilities. Terminal 3 construction elevates nominal port capacity to 4.5 million 20-foot equivalent units. However, maximum rail evacuation capacity remains structurally capped below 1 million units. This mismatch forces over 65% of containerized cargo onto the regional road network. By 2025, the structural deficit between actual port throughput and rail capacity will reach 1.95 million units. The physical bottleneck has shifted from the sea to the rails. The landside bottleneck is driven by severe technical and operational deficits across the Polish rail network. Freight trains managed by PKP PLK average just 25 kilometers per hour. This speed is 50% slower than German rail and 58% slower than Dutch networks. Priority conflicts with passenger services cause 45% of all freight delays. Furthermore, only 64% of the Polish network is electrified. Critical southern border crossings to Slovakia and the Czech Republic remain restricted by substandard axle load limits. These infrastructure deficits neutralize the geographic advantage of the Baltic Sea route. Rail transit from Gdansk to Prague takes 3.5 days, compared to just 1.5 days from Hamburg. Shipments to Budapest face an average of 30 hours of administrative and track priority delays. This administrative and physical friction forces 65% of Central European cargo onto roads. Relying on road transport inflates logistics costs by up to 24% per container. Without dual-track electrification to the south, Northern European ports will maintain their competitive dominance. Generation 4 lead-cooled fast reactors represent a major shift in nuclear engineering. However, their viability is bound to a highly concentrated metallurgical supply chain. Bismuth is a low-volume byproduct of lead and tungsten smelting. This makes its global supply highly inelastic. In 2023, China controlled 84.7% of global refined bismuth production, yielding 17,200 metric tons. Meanwhile, refining capacity in the rest of the world contracted by 11.4%. This concentration leaves Western advanced nuclear strategies structurally dependent on Chinese industrial infrastructure. The physical scaling of lead-cooled fast reactors requires immense volumes of heavy liquid metal. Lead-Bismuth eutectic coolant is highly dense, weighing over 10,300 kilograms per cubic meter. A single 300 megawatt electric small modular reactor requires 1,800 metric tons of coolant. This translates to 999 tons of high-purity bismuth. Scaling to a utility-scale 1,000 megawatt reactor increases the bismuth requirement to 3,330 tons. This single installation would consume 16.4% of total global annual production. The sheer mass of these requirements exposes a severe mismatch between reactor design ambitions and physical material availability. Projecting deployment scenarios through 2035 reveals a structural deficit. A moderate build-out of 2,000 megawatts of reactor capacity will require nearly 20,000 tons of bismuth. This cumulative demand represents 86.8% of projected global annual production. An aggressive build-out of 4,000 megawatts would require nearly 40,000 tons, exceeding annual global output by 173%. Because bismuth is a secondary byproduct, production cannot scale independently. Increasing output would require an economically unviable expansion of primary lead and tungsten mining. Without alternative coolant development or massive supply chain restructuring, the scaling of lead-cooled fast reactors remains a physical impossibility. The mechanical limits of silicon wafer slicing are determined by the tensile strength of ultra-thin steel wire. To minimize material waste, photovoltaic wire diameters have shrunk 50% since 2015, reaching a physical floor of 35 micrometers. At this scale, the wire must withstand linear speeds of 80 kilometers per hour. This mechanical environment subjects the steel core to tension forces exceeding 2.5 gigapascals. Semiconductor-grade wire has stabilized at 50 micrometers. Shrinking the core further risks catastrophic tensile failure during high-precision 300mm wafer slicing. Western initiatives to build domestic semiconductor and solar supply chains face a critical single point of failure. The production of diamond wire is almost entirely concentrated in East Asia. Chinese and Japanese manufacturers control 97.4% of the 236 million kilometer global market. China alone has expanded its capacity to 210 million kilometers. Meanwhile, manufacturing capacity in the rest of the world contracted by 28.5%. This leaves Western wafer factories structurally dependent on imported consumables for daily operations. Minimizing kerf loss is the primary driver of wafer manufacturing economics. Photovoltaic wafer thickness has fallen 27.7% to 130 micrometers. This reduction requires thinner wires to prevent mechanical breakage during high-speed slicing. In semiconductor manufacturing, Reducing kerf loss to 80 micrometers maximizes the yield of functional chips per silicon boule. However, a single 300mm slicing run consumes 45,000 meters of wire. Any microabrasive non-uniformity along this length causes immediate thickness variation defects, ruining the entire batch. The transition to lithium-iron-phosphate battery chemistry has shifted the primary strategic bottleneck of the energy transition. The critical constraint is no longer lithium extraction, but the chemical purification of phosphoric acid. China is projected to control 3.8 million metric tons of purified phosphoric acid capacity by 2030. This represents 76% of the global total, up from 62.9% in 2020. In contrast, combined North American and European capacity will reach just 800,000 metric tons by 2030. This slow expansion is gated by high capital requirements and long engineering timelines. Building a single 100,000-ton purification plant requires up to $220 million. Commissioning these highly specialized solvent extraction facilities takes 36 to 48 months. The domestic deficit of battery-grade purified phosphoric acid is an active bottleneck. In 2024, Western battery-driven demand reached 65,000 metric tons, outstripping available domestic capacity of 35,000 tons. This deficit will expand to 635,000 metric tons by 2030. Regional demand is projected to scale to 980,000 tons, while domestic battery-grade supply reaches only 345,000 tons. Existing Western purification plants cannot easily pivot to support the battery sector. Over 90% of current capacity is legally locked into long-term supply contracts for food, beverage, and agricultural applications. Consequently, Western gigafactories scaling up lithium-iron-phosphate cell production face an immediate structural reliance on foreign imports. This dependency directly undermines regional supply chain localization initiatives. Chemical synthesis of lithium-iron-phosphate cathode material reveals why this intermediate chemical is so critical. Producing 1 metric ton of cathode active material requires 820 kilograms of purified phosphoric acid. This makes phosphoric acid the largest single input by mass, exceeding both iron precursors and lithium carbonate. At baseline market rates, this single precursor accounts for 21% of the total direct manufacturing cost. Achieving battery-grade purity requires reducing arsenic levels to below 5 parts per million and heavy metals to below 10 parts per million. This purification process relies on energy-dense solvent extraction, consuming up to 200 kilowatt-hours of electricity per ton. Without localized, high-volume purification capacity, the Western battery supply chain remains highly vulnerable. The transition to domestic electric vehicle manufacturing cannot succeed without securing this heavy chemical processing node.